Pure functions in Python are essential for advanced functional programming. They ensure code predictability by always producing the same output for the same input, without side effects. This allows developers to reason about code using algebraic principles, enhancing code reliability and maintainability in production environments. A pure function is defined by its deterministic output and lack of side effects. It consistently returns the same result for identical inputs and doesn't alter external states. This ensures referential transparency, allowing substitution with its return value. Pure functions rely solely on their input arguments, forming the basis of functional programming's algebraic reasoning. Pure functions like add are predictable and testable, always returning the same result for identical inputs. In contrast, impure functions, such as add and count, modify external state, complicating testing and introducing dependencies on execution history. Pure functions ensure consistent behavior, while impure functions risk unexpected outcomes due to state changes. Pure functions enhance testability by eliminating dependencies, making them easy to test. They support parallelization, allowing concurrent execution without race conditions. Their deterministic nature aids in reasoning and enables caching through memoization, ensuring efficient performance by storing results for identical inputs. Avoid I/O operations like file reading or network requests, as they breach purity. State mutation, such as altering global variables or input arguments, disrupts function purity. Randomness and time dependency introduce non-determinism, violating pure function principles. Exception handling, while sometimes necessary, can also be a side effect in strict functional programming. Building pure functions involves ensuring that each function relies solely on its inputs, avoiding global state, mutations, and I/O operations. For instance, calculate total with tax computes, a total using only provided items and tax rate, while format currency transforms numbers into strings. These functions compose cleanly, maintaining purity by having explicit dependencies in their signatures. Mutable data can lead to unexpected side effects. Consider add item impure, which modifies the input list, breaking referential transparency. In contrast, add item pure returns a new list, preserving the original. While the pure approach may appear less efficient, it prevents hidden dependencies and reduces bugs, ensuring more predictable and maintainable code. Tuples are immutable sequences, ideal for data that shouldn't change, offering speed and safety in concurrent environments. Frozen sets, like frozen set, Python, FP, are immutable and can be dictionary keys. Strings are inherently immutable, with operations like text.upper returning new strings. Use frozen true in data classes for immutable objects with automatic equality and hashing. Immutable data structures in Python allow updates by creating new instances. Use replace for data classes, ensuring the original remains unchanged. Python 3.9 Plus offers the merge operator for dictionaries, enabling non-destructive updates. For lists, use unpacking or comprehensions. Libraries like Persistent enhance efficiency with large datasets, maintaining immutability while allowing updates. Referential transparency allows replacing a function call with its result without altering program behavior. For example, square 5 can be replaced with 25, enabling optimizations like memoization and parallel execution. This property is crucial for efficient computation, as it allows compilers to optimize code by caching results and performing lazy evaluations. Higher-order pure functions like map, filter, and reduce enable declarative data transformation. Map applies a function to each element, filter selects elements based on a predicate, and reduce combines elements into a single value. These functions maintain purity by accepting and returning pure functions, allowing for efficient, loop-free data processing. Function composition allows us to build complex operations from simple, reusable functions. By composing pure functions, we create a data transformation pipeline, ensuring each stage is independently testable. For example, using composition, we can normalize text by stripping whitespace, converting to lowercase, and removing punctuation, resulting in a clean, consistent output. Memoization optimizes performance by caching results of pure functions. Using ALRU cache, functions like Fibonacci and expensive calculation store results for repeated inputs, reducing computation time. Ensure arguments are hashable, like tuples, for effective caching. Remember, memoization is only reliable with pure functions, as side effects or external dependencies can lead to incorrect results. Isolate side effects by pushing impure operations to the system's edges, maintaining pure core logic. Separate computation from input-output. Pure functions compute, while separate functions handle input-output. Use dependency injection to pass external dependencies as arguments. Pure functions can return data structures for side effects, executed later, controlling where side effects occur. Dependency injection enhances testability by making dependencies explicit. Instead of directly calling I/O functions, inject them as arguments. This separates pure logic from impure operations, allowing easy testing with mock functions. For instance, process user pure uses a fetch function parameter, enabling both mock and real data retrieval, ensuring clear, testable code. Pure functions in data validation ensure consistent and reliable results. The validate email function checks for presence, format, and length, returning a validation result. The validate user data function combines multiple validations, ensuring name length and age validity. These functions are deterministic, making them ideal for testing and ensuring data integrity without side effects. Testing pure functions offers simplicity and efficiency. With no need for mocking, setup, or teardown, tests remain isolated and deterministic. Inputs consistently yield the same outputs, ensuring reliability. Pure functions facilitate property-based testing with tools like Hypothesis, allowing random input generation to verify properties. This approach enhances test speed and accuracy, crucial for robust software development. Creating new data structures instead of mutating can lead to memory allocation overhead, impacting performance. Libraries like Persistent use structural sharing to minimize this. Lazy evaluation with generators and ITER tools reduces memory usage by computing values on demand. Memoization trades memory for speed, so monitor cache hit rates. Profile before optimizing. Pure functions often benefit from compiler optimizations. In a data transformation pipeline, we use pure functions to ensure immutability and testability. Transactions are filtered by date, then aggregated by category. The generate report function composes these transformations, producing a report with total amounts and counts. This approach maintains purity, enabling predictable and efficient data processing. Avoid hidden state access by passing dependencies explicitly. Prevent mutating input arguments by creating copies for transformations. Instead of using exceptions for control flow, employ result types or optional values. Refrain from calling datetime, now, or random.random within pure functions. Pass these values as arguments to maintain purity. The functional core, imperative shell pattern, optimizes software design by separating pure and impure components. The core handles business logic, data transformations, and validations, ensuring testability without mocks. The shell manages input-output operations like database queries and application programming interface calls, feeding data to the core and handling results. This approach leverages pure functions while accommodating necessary side effects. Type hints in pure functions ensure clarity and safety. Use typevar for generics and protocol for structural typing. Immutable data, like immutable user, prevents side effects. Functions like maplist and process data use type hints to document purity, employing immutable types such as tuples. This approach guarantees predictable behavior and enhances code reliability. In performance-critical code, like with NumPy, mutation is acceptable if isolated. Logging, while a side effect, aids observability without affecting correctness. Frameworks like Django may require imperative styles. Use pure functions within handlers. Always document purity violations, keep side effects explicit, and favor immutability. Pragmatic purity ensures maintainable code over theoretical perfection. Explore essential tools for functional programming in Python. Tools and SciTools offer composable functions for data transformation. PyRsistent provides immutable data structures, ideal for functional style. Returns introduces monads like maybe and result for handling errors. Hypothesis excels in property-based testing, generating random test cases to verify function properties. Designing for purity involves defaulting to pure functions, ensuring core logic remains testable. Isolate side effects by pushing impure operations to system edges. Embrace immutability for clarity and safety, often outweighing performance concerns. Compose functions to build complex operations from simple, reusable components. Balance functional principles with practical constraints for reliable software.